I want to talk a little bit about methods for approximating functions, because the reality of life is when we make mathematical models, especially mine, you end up adding in all sorts of great assumptions about the underlying biology of the system, and you can wind up with a model that's kind of a horrible mess that you might not know how to evaluate at places that are interesting, or it might have an asymptote near values you might find interesting, or not exist at values you find interesting. So there are lots of mathematical tools we have that let us make a pretty good guesstimate of what our function is going to do near a value that we're interested in. So the approximation method of sort of first resort is always linear approximation, which approximates your function by giving you the equation of the tangent line to that function at the point you care about, which probably will make more sense if I draw you a picture. If I have some function of x, and I want to know the value of my function here at some point a, I might not be able to find the value of f of x, so this is f of x. But what I can do is I can find a tangent line at that point. The slope of this tangent line is given by the first derivative, which we remember. So if you look at it, right, the tangent line is going to be really close to f of x, near to the point I care about, near to a. So even if I can't evaluate the function at the point I care about on the function, I can evaluate it on the tangent line and get a pretty good close guess. So to do a linear approximation, first, you need to find the derivative of your function that you care about with respect to x, and pick your point where you want to approximate the function. And then because you have to get the tangent line, this thing here, because you have the slope of your line and a point on the line, you can get the equation of the line. I know we're going back to high school here. So the slope of your tangent line is going to be given by y minus y1 being the point that you have, is equal to the slope times x minus x1. So y is just f of x, y1 is this f of a point we have, is equal to the slope, which is f prime at x. Sorry. F prime at a, our point, times x minus a. And our little rearrangement gives us that f of x is equal to f of a plus the derivative at a times the difference between x and a. So at a, this is fundamentally true. Close to a, it's a reasonable approximation. As a fun aside, you can also convince yourself that this is true close to a, by just rearranging the definition of the derivative, right? If f prime of x is equal to f at some place close to x minus f at x all over h, and remembering from over here that a is x is some number close, a is some number close to x, and you can just rearrange it again, and you end up with f of x is equal to f at a plus f prime at x times x minus a, and since f prime at x is going to be equal to f prime at a, then you get back this expression, f prime at a. Not so bad. So as I said, linear approximations are the first, I want to say line of defense, but that doesn't make actual sense. They're the first resort when you want to approximate something. But even just looking at my sort of crappy sketch of functions here, you can see that the further away from the point at which you built your approximation, the further away from A you get, the further away your tangent line is going to be from the function you're trying to approximate. So the error of a linear approximation gets quite big quite fast as you get further away from the interval where you started. So what do we do if we want to make our approximation better? Well, it would be great if instead of a straight line tangent at our point, if we had something that curved a little bit, that had at least the same concavity as our function, right? Concavity is what the second derivative tells you. It tells you whether the function was increasing or decreasing at that point. So we can improve our approximation by adding more derivatives to it, if that makes sense. I'll show you what I mean. I'm just going to draw my little function again. So I have some function, f of x, x and y. And I want to approximate its value at some point a. Then the linear approximation is the tangent line to the curve, but we want to do one better. We want to get a curvy-looking approximation that has derivatives in the same, second derivatives that give it the same concavity as the original function, so that it stays closer to the original function for a bigger interval around a. F at x is kind of equal to the linear approximation, function at a plus its derivative at a times x minus a. And our quadratic term, quadratic just means it has an x squared in it somewhere, is going to be the second derivative at a times x minus a squared all over 2. So you may have noticed what I'm actually doing here is making a Taylor series expansion around f at a, or around a, I should say. Right, because the equation for a Taylor series, f at x is equal to function at a plus first derivative times x minus a plus f double prime at a times x minus a squared over 2 plus f triple prime at a times x minus a cubed over 3 factorial. This is actually a factorial, and there's a 1 factorial, and there's a 0 factorial, which is the sum from I is equal to 0 to whenever the ith derivative of a over I factorial times x minus a to the I. Now, just in case you're going, whoa, what the hell is a series expansion? I'm going to talk about those for a second. You can skip this next bit if you remember sequences in series. So this is an aside about series. Sum series S is just a sum of a bunch of numbers, like 2 plus 4 plus 6 plus 8, dot dot dot. So if I write the dot dot dot, that implies it goes off to infinity, or to whatever's after the dot dot dot. Let's say for now there's no dot dot dot. So my series is just 2 plus 4 plus 6 plus 8. This is what's called an arithmetic series, because it's just your first term plus some constant plus some constant plus some constant. So we can say that that's this big sigma is the notation for series. We say from I is equal to 1 to I is 1, 2, 3, 4, so it's 4 terms. It's the sum of all numbers given by 2i. And if you want to evaluate a series, an arithmetic series, the sum is just the number of terms divided by 2 times the first term plus the last term. A is usually what's we use to describe A with a subscript to describe the term in a series. Most of the series that you're going to deal with are going to be the other kind, where you get, say, 2 plus 4 plus 8 plus 16 plus 32. Right, these are all, each term is the one before it multiplied by 2. So that's a geometric series, right, which is just 2 plus 2 times 2 plus 2 times 2 squared plus 2 times 2 cubed plus da-da-da. So we're going to say 2 is our A1 and 2 is R, the ratio of each term to the one before it. So in general, the solution, this kind of series is given by the total sum for n terms if you have a geometric series k terms long, its sum is given by this, and if it's an infinite series where n goes from 1 to infinity, it's just the first term divided by 1 minus r. So when we go back and then look at this expression for Taylor series expansions I showed you, you can see when you do the derivation for a Taylor series, what you start with is deciding that you want to make a geometric series expansion of your original function. I'm not going to do the derivation in this video, but there are links out to resources that do it if you would like to see. And I just realized I made an important mistake here. The definition of the Taylor series, the full Taylor series, goes to infinity. Right. By definition, if you take the infinite Taylor series, it will be exactly equal to f of x. It becomes an approximation when you truncate it and only use the first n terms. This is important. So the general rule when you're doing a Taylor series expansion to approximate your function is, most of the time, the more terms you use, the better your approximation is, the closer it'll stay to your original function, and the bigger an interval around a it'll be good for. So when you're actually making your approximations, the one with x squared, right, f of x is sort of equal to f at a plus f prime at a times x minus a plus f double prime at a times x minus a squared over 2. This is the quadratic version of the Taylor series. And this is what we call a second order term. This is a first order term. This is a 0th order term, because the order of magnitude of the x minus a terms. You can imagine there being an x minus a to the 0 here, right? Most of the time this is as far as you have to go, because also there's a sort of law of diminishing returns here. If you add the third derivative term, it may get to be the point that evaluating your Taylor series is a bigger pain in the behind than evaluating the real function, or it might actually start to diverge from the original function. There are lots of reasons to be careful when you're deciding how many terms to keep, or how many terms to use, I should say. So in general, if you want a kind of quick and dirty approximation, you use a linear approximation. If you need something to be valid over a wider interval, or maybe even closer to the original point, then you can use a quadratic approximation. If you want to be really, really accurate, or you want to be over a wide interval, or some other special cases, then you might want to use higher order terms. So a lot of the time, when you're using an approximation, you're not really trying to approximate a function at a point, you're trying to approximate it over an interval. You want to know what the function's going to do when, say, x is small, or when it's between some value and some other value. So it's really important to be able to put a number on how good your approximation is, what the error bounds are around your approximation. So how good is your approximation? You've got some function x, and you've got your Taylor series approximation with n terms, and you want to know how close it is to your function on the interval you're interested in. You want to know what the difference is between the value of f at x and the value of your expansion. So just notation-wise, let's call our Taylor approximation with nth degree terms Pn. So the difference between your function and your approximation is called error. And if you think about it, just for a second, oh, and also, we only really care about the absolute value of it, right? Because if it's positive or negative, it's still error. We just want to know how big it is. If you think about it for a second, the full Taylor expansion is the sum from I is equal to 1 to infinity of all of this stuff. F at a, f I times x minus a to the I over I factorial. And your approximation is the sum from I is equal to 1 to n. Oh, actually, I goes from 0. Sorry, there's a 0th order. I always forget that. Right, because f to the 0, a is just f at a. That's that first term. Anyway, so your approximation, Pn, is just the same thing but for only n terms. Which means the error is just, sorry, it's not a squiggly line, it is all the terms you didn't use, I from n to infinity of your function, of the Taylor series expansion. Alright, so if you've done a quadratic approximation, which goes up to n is equal to 2, from 0, 1, and 2, then the error is just going to be the rest of the terms from 3 to infinity, all summed together. So how do we get a handle on what all the other terms are going to be, since we've decided to omit them? Rather than evaluating the full Taylor series, which may not even be possible depending, you can get an idea of what the maximum possible error is given your expansion. I'm just going to straight up give you the expression. So if you have an nth order Taylor approximation, the error looks an awful lot like the expression for the very next term with one key difference. So it's the n plus 1th derivative at some point z times x minus a to the n plus 1 over n plus 1 factorial. So the next term up would have just been fn plus 1 at a. So z is some point between x and a. So it's in the interval that you're approximating, and it's whatever the point is where f triple prime at z is a maximum, right? Because you want to have you don't want to underestimate your error. You want to make the maximum possible error is the error at the point where f at n plus 1 is a maximum. How do you find that? Sometimes you might just know, like if it's a trig function where quite often derivatives are 0 or 1, you'll know where it's going to be 1, and that's the maximum. If you don't know, you probably know how to find the point for which some function is a maximum, right? You find the critical points of fn plus 1 of z, and then pick a value of z that is the critical point that is the local maximum. And if you're not sure how to find a local maximum, I think there's a video about that. So when you're estimating your error, you can use this expression And pick your value of z, which is a point that makes fn plus 1 z a local maximum between x and a. Now I'm going to do a quick example just so you see what all of this series expansion stuff could possibly be useful for. I'm going to make a Taylor series approximation for e to the x when x is small and find its error bounds. So let's approximate e to the x when x is between 0 and 0.1, say. I'm only going to use the first 3 terms of my Taylor series and then assess how much error I'm making by truncating the rest of those terms. So e to the x is going to be sort of equal to function at 0 plus f prime at 0 times x minus 0 plus f double prime at 0 times x minus 0 squared over 2. Since all of the derivatives of e to the x are e to the x, this is easy. We just get e to the 0 plus e to the 0 times x plus e to the 0 times x squared over 2, which is 1 plus x squared. The error on the interval 0 to 0.1, the n plus 1th derivative at some point z times x to the n plus 1 all over n plus 1 factorial, which in this case n plus 1 is 3 because I've used the first 3 terms. So f triple prime at some point z times x cubed all over 3 factorial. So now we have to pick what our point z is going to be. We want to know what the maximum over the interval x is 0 to 0.1. The maximum value of f triple prime of x, so the maximum value of e to the x is just going to be e to the 0.1. Right? E to the x is a strictly increasing function between 0 and 0.1, so the value at 0.1 will be the highest. So back over here, that means our error bound is going to be e to the 0.1 times 0.1 cubed all over 6, which gives us something like 0.10001842, I think. And if we check it, we see that e to the 0.1 is actually equal to 1.10517009 . Using our approximation, e to the 0.1 sort of equals 1 plus 0.1 plus 0.1 squared over 2, which is equal to 1.105. So the actual error at that point is 0.17, blah, 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 blah. So I picked this example because quite often in the literature you'll see e to the r replaced by 1 plus r in population dynamics equations, where r is the growth rate. What people are doing is using the linear approximation, 1 plus x, of e to the r, which has a pretty good error bound when r is sufficiently small. So for here, the linear approximation would just be 1.1, which has an error of about 0.005. So that's still not bad. And depending on the application, an error bound of 0.005 might be fine. Sometimes you might need something more precise, so the 0.0000184. So you might want to include the quadratic term. There are plenty of other methods for approximating functions. These are the 2 most commonly used ones, so I've introduced them to you today. We learned about the linear approximation. We learned about quadratic approximation and higher order approximation, which were all fundamentally Taylor series expansions. And we learned about putting error bounds on our approximation, which is very important, to make sure we're not using an approximation in a domain of X where it's not really that valid. And I reminded you why we sometimes say e to the r is sort of equal to 1 plus r. And if you'd like to see more derivations or more examples, there should be some good materials in the Further Reading and Resources page.